Today we're going to do a demonstration on luminol. It's a pretty cool reaction that demonstrates some really cool spectroscopy. This video is aimed for a general chemistry course with the mechanistic analysis aimed for an organic chemistry course. If you have not watched my first video on phosphorescence, I would suggest you do so before watching this video, as there are several concepts in that video that I will refer to in this video that are important for understanding the luminol demonstration. So let's talk about luminol. The luminol reaction is a chemiluminescent reaction. It's often used in forensic analysis, and that's because iron acts as a catalyst in the reaction. So, as you should know, blood contains iron. So when a solution of luminol and an oxidizing agent is sprayed on a crime scene, the areas contaminated with blood will light up, like in the handprint shown to the right. Luminol is a chemiluminescent reaction, and chemiluminescence has the same principles as photoluminescence. As you should have learned from my last video, that includes fluorescence and phosphorescence, where the electron in the atom is excited by a photon of light to a new energy state, then relaxes back down to the ground state, emitting electromagnetic radiation or light. But in chemiluminescence, the electron is excited by a chemical reaction rather than light. So if you look at the firefly to your right, that is a biological example of chemiluminescence. So in the firefly's case, it is referred to as bioluminescence. For a chemiluminescent reaction to occur, there are several requirements. So first, the reaction must provide sufficient energy to create the excited state. The reaction must produce a species capable of forming an excited state, and the reaction must follow a mechanism that favors the production of excited state over ground state. I mentioned that the luminol reaction is an oxidation. In organic chemistry, this is generally defined as an addition of oxygen, which generally gives higher energy complexes. And in oxidation, the compound that does the oxidizing is the oxidizing agent. We have the mechanism of the oxidation of luminol. Luminol is a diamide, making it much more acidic than the common amide, allowing it to be deprotonated by a common base. In our case, that is carbonate and bicarbonate. If you look at the dianion, the second structure, you see that both nitrogens are now negatively charged. These electrons can kick down and create a nitrogen-carbon double bond, and then push the double-bonded electrons from the carbonyl up to the oxygen, giving the negatively charged oxygen complex you see in structure 3. But what is important to note is the double arrow between the second and third structures. That represents resonance, so it's just telling us that those two structures are the same molecule, they're just a different representation of how the electrons can be in the molecule. The next step is for the dianion, which is the third structure shown, the resonance structure of structure number 2, to react with hydrogen peroxide. Iron 3 is present in the reaction. The ions serve to catalyze the formation of molecular oxygen from hydrogen peroxide. And molecular oxygen is what's actually going to react with the dianion. Just a reminder, a catalyst is in a reaction to lower the activation energy of the reaction so that it occurs at an observable timescale. And the iron serving as a catalyst is not actually consumed in the reaction, but it is regenerated in the end. The reaction with the molecular oxygen and the dianion creates a cyclic peroxide, which is not shown, but what's important to note is that the cyclic peroxide is a very high energy. The cyclic peroxide rapidly decomposes, and because it had such high energy, it decomposes into the 3-aminophthalate ion, but in its triplet state. So as a refresher, the triplet state is where the electron in the ground state and the excited state are unpaired spin-wise, therefore they have the same spin. Then the electron has to go through an intersystem crossing back to the singlet state before it can relax down to the ground state. As a refresher, singlet state is when the ground state and excited state electron are paired spin-wise, meaning they have opposite spins. Because the electron is back in the singlet state, it can relax back down to the ground state and emit light. If you look at structure number 6, it is the same as the other dianions on the bottom. The difference is the electron is now back in the ground state. So if you look at these energy level diagrams, both electrons are in the ground state, paired spin-wise. And And as you should have remembered from my last video, because the electron was in the triplet state, the light emission is phosphorescence. We are going to do an interactive exercise. I've put the blank mechanism back up on the screen. I want you to draw arrows of the deprotonation by base, the resonance between the two dianions on the top, label the resonance arrow, label the arrow for intersystem crossing, and label light emission. Pause the video and start working on the mechanism. By now you should have drawn out the mechanism. If you haven't, you're cheating, and go back and do it because I don't condone dishonesty. So here are the answers. If you got any part of the mechanism wrong, I would encourage you to go back to the earlier part of this video and check your mistakes. Now to the cool part, the actual demonstration of luminol phosphorescence. I've just placed a beaker onto the stir plate with just about 100 milliliters of water. Right now I'm adding hydrogen peroxide, 3%. It's the same concentration as what you can buy in the grocery store. That's going to be the source of molecular oxygen that reacts with the third complex shown, the dianion, to give you your triplet dianion that will eventually phosphoresce. Right now I'm adding the carbonate, bicarbonate, and luminol mixture. So those together will react and form the dianion that you see in complex 2, which is the two negatively charged nitrogens. And now comes the cool part. I'm just about to add potassium ferrocyanide, source of iron 3 for catalysis, to make it glow. And now we have phosphorescence. It's a pretty cool reaction if I say so myself.